Okay, so we're beginning Unit 8, Secondary Math 2. Today we're going to start to talk about the quadratic formula. Before we do that, I want to mention that these are pieces of the Guaranteed Viable Curriculum, or the GVC, that we have in our district, which means that it's a big deal. These are key pieces that we need to make sure that you understand really well as you leave Secondary Math 2. Okay, so the GVC for this statement is that I can solve quadratic equations by factoring. That's something that we've already been doing. Factoring is helpful in solving certain types of quadratics. The solutions that we can get when we factor generally are just rational numbers. So that's a lot of answers that we can get, but it doesn't give us all the answers that we want. So essentially, rational numbers are integers. Like those, any whole numbers and their opposites are integers, and it's fractions, right? Any number that you can write as a fraction, a over b, where a and b are both integers, except b can't be 0. So these are the types of answers we can get when we're factoring. It doesn't give us all the answers, but it's helpful. The benefit to factoring is it's pretty quick. So it's a nice, easy way to solve quadratic equations, but it doesn't always work. So then we looked at taking the square root. These are especially helpful if you can get to a place where you have x squared equals number, or even if you can get to some quantity squared equals number. Now, we had some problems can't be solved in this way, at least just with this method. If you had x squared plus some linear term with just an x in it, no second power, but x to the first degree, if you're dealing with that situation, then it takes a little bit more work to be able to solve using square root, so just taking the square root doesn't work in this situation. However, the benefits to solving by taking the square root is we can get all kinds of answers now, not just rational answers, but we can get radical answers. So some square roots of things can happen, and we can also get complex answers where we could have something like 3 plus or minus I root 2. These are not the types of answers that we could have gotten from factoring, but we can get them when we take the square root. And square root, when we have a linear term, that's the sort of stopping place for square root. So that leads us to a third method, which is completing the square. This was especially helpful when we did have a third term, right? So if we had something like x squared plus 6x plus any number, we'll say 7, then we solved this by moving the constant to the other side of the equation. Then we had these things here. We were looking for building a perfect factor so that if we take x plus something times itself, that we would get x squared plus 6x plus something. Okay, so I know that if I take x plus 3 times x plus 3, I will get x squared, and then if I take outside 3x, inside 3x, together that will be the 6x that belongs there. I just need to add in this final piece. So in this case, it would be 9, right? It's going to be the square of whatever that was. And we found this number 3 by taking half of that value, half of the b value. Whatever I add on this side, I have to add also on that side. That makes our equation still true. So then we had, like x plus 3 squared equals, let's see, negative 7 plus 9, that's 2. Now we have quantity squared equals number. Now we could take the square root of both sides. Okay, so completing the square works for all types of problems as well. The disadvantage on completing the square can be that if our b term is not even, then we're dealing with a lot of fractions, and sometimes that can make things a little bit challenging. So while it can solve all types of quadratic equations, sometimes it's not the easiest method to deal with. So finally, we're going to find the quadratic formula. We're going to derive that formula by completing the square. And it takes care of any type of quadratic equation. So we're going to start with ax squared plus bx plus c, which is just the standard form equals 0, standard form of a quadratic function. Now, as long as a does not equal 0, then we can use this quadratic formula. If a does equal 0, then this entire term, ax squared, will go away because 0 times x squared is just 0, and then we wouldn't have a quadratic function anymore. It would be linear. It would be a line like what we did in secondary math 1. Okay, so that's the introduction. You may be thinking to yourself, well, if quadratic formula takes care of all of them, why did we bother learning the other 3 methods, and or why are they important? And in my opinion, quadratic formula is the option of last resort. It's time consuming, it's a little bit clunky to get through. So if you can factor, or if you can see that taking the square, completing the square are going to get you there more quickly, those are the ones I would default to. However, for this unit, we are going to practice quadratic formula a few times. So we'll just get used to using it, and then after we're comfortable with it, then we'll remind ourselves of all the ways that we know how to solve and be strategic about choosing the way that's going to lead to, or that's going to be sort of the quickest, most efficient for solving. Okay, let's derive the quadratic formula. So what I've done here is I've got the standard form of the quadratic function with ax squared plus bx plus c. And essentially what the a, b, and c mean is I can put any number in those places, except a can't be 0, any number in there, and I will be able to solve this and get the answer. So it's going to work for all situations. And then I put this real number problem here, it should have said equals 0, so that we can remind ourselves of how we're getting these steps, and it's not just random. Okay, so we're going to pretend that we want to solve this equation on the right by completing the square. I should say equals 0. So I'm going to start by moving the constant to the other side of the equation. So I'll have 3x squared plus 5x. I'm going to leave some space. I like to do that. Equals negative 10. If we do that same thing over here with the quadratic formula with the letters, that will work for any function, the constant that we want to move is the c. So I'm going to subtract c from both sides. Then we'll have our quadratic term and our linear term, the ones with the variables, over on the left side of the equation. And on the right, we'll have equals negative c. Okay, moving back to the one with numbers. To complete the square, we want to have a equal 1, and right now it's 3. So I'm going to get rid of that 3 in that place by dividing every single term by 3. So we'll have x squared plus 5/3 x equals negative 10/3. Okay, if we apply that to our equation with the letters, I'm going to divide every single term by a, so that we just have x squared plus b over ax equals negative c over a. Okay, to continue by completing the square, what I like to do is think of what's the term that I want in here. It's some number that when I add it to itself, I get 5/3. Now, if we had a number like 10, that would be easy to see. 5 plus 5 equals 10. 5/3 isn't quite as obvious, but we can use the same math that we did to get 10, and we can do it here. That we used to get 5. So if 10 were my middle term, 5 plus 5 equals 10. How do I go from 10 to 5? I'm dividing it by 2. So we're going to do the same thing with 5/3. I want half of 5/3. So if I take 5/3 divided by 2, or if I do 1/2 of 5/3, either way I'll get 5/6. So essentially I'm just multiplying the denominator by 2. Now remember, this does not equal this yet. in order to make those two equal to each other, I need to add the square of this number. So I'm going to add 25/36 to both sides of the equation. I'm going to pause right there for just a second while we think through doing the same thing on this side. So I want half of this. That's what's going to build my perfect square. And it's going to be b over 2a. To get the number that belongs here and here, I'm going to square b over 2a. So I'm thinking of b over 2a times b over 2a, and I will get b squared over 4a squared. Okay, we'll pause on that one for a second. Let's head back over here. Our calculators probably can handle this addition of fractions for us pretty easily, but I think it's worth seeing how we get there mathematically because we're going to be doing the same process on the other side. So what I'm going to do is I want a common denominator. Right now my denominators are 3 and 36. If I multiply 3 by 12, it will become 36. And I want to multiply the numerator by 12 as well. That way I'm multiplying by 1. 12 twelfths equals 1. And it's not changing the value of the fraction, but it is changing the look of it. So what I'll have here is, let's see, negative 10 times 12 is negative 120. 3 times 12 is 36. Plus 25, 25/36. Okay, now that we have a common denominator, these two are easy to add together. I will get negative 95/36. And over here, I still have my x plus 5/6 squared. Okay, we'll come back and finish this in a second. Let's pop over to this side. Right now, I don't have a common denominator here, but I want one. So a and 4a squared, if I multiply some stuff to the a, I might be able to get it to equal 4a squared. So think to yourself, what is it that I need to multiply that by to get 4a squared? A times what is 4a to the second power? Well, it's going to be 4a. And if I multiply the denominator by 4a, I need to multiply the numerator by a. That way I'm multiplying by 1 and it doesn't change value, it just changes its look. So this is going to be negative 4ac on the numerator and 4a squared on the denominator. And we're adding that to b squared over 4a squared. Okay, let's go ahead and put that together. So we have x plus b over 2a squared. Now to get this to look like the traditional formula, I'm just going to swap these two. So I'm going to write b squared over 4a squared first. Doesn't change its value, I'm just changing the order. Minus 4ac over 4a squared. I'm only doing this because this is how it conventionally looks. We're used to seeing it in this way, so I'm just making that switch right there, but it doesn't change the value of anything. Oh, what we can do too is since we have a common denominator in both cases, just like we did over here, we can put the numerators together. Negative 125 plus 25 is negative 95, and the denominator all over one thing. So let's pop back over here and do that. So we're going to get b squared minus 4ac all over this common denominator of 4a squared. Okay, let's head over to the one with numbers. At this point, we've got something squared equals number, so I can take the square root of both sides. I will get x plus 5/6 equals plus or minus the square root of negative 95 is, let's see, I'm not sure. Let's try negative 95 divided by 25. 95 divided by 5 is 19, so those are both prime. So root 95 is going to stay square root of 95. The I goes out front because of this negative sign right there. And then our denominator, the square root of 36, is just 6. So we're in good shape there. Okay, back over to this one. We'll take the square root of both sides. We'll have x plus b over 2a equals. Now our numerator is messy. There's not a perfect square that we're going to use there, so we'll just put the whole thing under the radical symbol. But the denominator, 4a squared, this can be square rooted. 4, the square root of 4 is 2, and the square root of a to the second power is a. Okay, pop back over to our number. To get x alone, we need to subtract 5/6 from both sides. So I'm going to subtract 5/6 here, subtract 5/6 there. Look at this, we have common denominators. So I'm going to put the numerator all together, -5 plus or minus I root 95 all over 6. Yeah. Let's do the same thing on this side. I'm going to subtract b over 2a from both sides so that we get x alone. Common denominator, 2a and 2a, so this whole thing can go together. So we'll have x equals -b plus or minus the square root of b squared minus 4ac all over 2a. All right. There's a song that you can sing with this to kind of help you memorize it. It's like the melody of All Around the Mulberry Bush. So it's like x equals -b. Let's see, I'll highlight as I go. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. Okay. In class, I made the students sing it with me 3 times after I sing it a couple times, just so that we could get used to it, because having this memorized is going to be helpful when you're completing the test or coming across other quadratics that you want to solve that aren't easy to solve another way. Okay, we kept going with this lesson and spent some time focusing on something called the discriminant. The discriminant is the part of the quadratic formula that showed up under the radical symbol. That was b squared minus 4ac. Okay, this number is super useful to us because it helps us to see how many and what type of solution we can get using the quadratic formula. And it's good practice to get used to finding this so that when you're actually using the quadratic formula, this is like a first step in how you go about solving it. So we're just going to practice using the discriminant. I created a worksheet for us to try with this in mind. Here it is, discriminant worksheet. So this says find the value of the discriminant of each quadratic equation. So again, the discriminant is a part of the quadratic formula. If I were you, I would write this at the top of this worksheet because it's going to be the thing we're using today, b squared minus 4ac. That was under the radical symbol in the quadratic formula. Okay, so how do we use this? Well, first you want to identify a, b, and c. Well, maybe first you want to get it in standard form. This one's already there. We've got something, let's see. We have our quadratic term, linear term, constant term equals 0. Okay, it's already in order, set it for us just like we like. So what I'm going to do now is identify a, b, and c. So remember that standard form looked like ax squared plus bx plus c equals 0. I'm just going to replace each of these letters with the number that we get from the equation. So in this case, a is the coefficient of the quadratic term, -5. In this case, it's -5. A is always the coefficient of the quadratic term when it's in standard form. The coefficient of the linear term, that's our b value, 4. And then the constant is our c value, 4. Okay, so what I would do at this point is write b squared minus 4ac. You're going to want parentheses around each of the letters. Okay, now all of this that I've written is useful. This is useful, especially if identifying a, b, and c is a little bit tricky for you. Okay, then I highly recommend that you take the time to write down what a, b, and c are. As you get used to practicing this, you might be able to just simply recognize them without needing to write it down, so that's fine. But this next part I absolutely want you to write. I want you to write whatever b is in this first parentheses. So in this case, it's 4. Then we're just going to keep using this formula. Minus 4, parentheses. Now instead of writing the letter a, I'm going to write what a stands for. In this problem, it's -5. And then finally, I'm going to plug in c. This is going to be 4 right there. This is a great chance at this point to practice your mental math if you want, but I also recommend that you plug it into the calculator. It's really easy to make small arithmetic errors as you're working here. So this one, let's see, -4 times -5 is +20 times 4, that's positive 80. And right here would be 16. As you plug it into the calculator, this number in front of the 4 must be minus. Please don't put a negative in your calculator there. It will multiply everything together instead of subtracting the second part. So watch for your minus right there. But inside the parentheses, these numbers, that's going to be a negative 5. Okay, so take a second if you want, plug this into your calculator. You should end up with 96. Okay, let me see if there's one that's slightly challenging that we've got out of here. Maybe let's do number 4. If I'm identifying A, B, and C, then I can see that the coefficient of the quadratic term is negative 4. The coefficient of the linear term seems to be missing, but it's not 0. If it were 0, then I'd have 0 times n, which is 0. The n wouldn't be there at all. So instead, the thing that's written there that we never bother writing in, that's there but we don't write, is 1, right? So the coefficient of the linear term in this case is 1, and our constant term is 1. So now we're going to use b squared. So b is 1 minus 4 times a, that's negative 4 in this case, times c, that's 1 in this case. So we will have 1 squared is 1, plus negative 4 times 1, that's 16. Our answer should be 17 on this one. And once again, go ahead and check that with your calculator. This is minus 4 always. And this one, any in the parentheses, these are negative. Okay. All right. Next part takes things up slightly. So right here it says find the discriminant of each quadratic, then state the number of real and imaginary solutions. Okay, so this will take us one step up. Before we begin identifying A, B, and C here, we need to put this in standard form. Can you see what about this makes it so that it's not in standard form? It's the equals 9. We need this to be equal to 0, and then we're in good shape. So let's subtract 9 from both sides. We'll have k squared minus 7k plus 6 equals 0. Okay, so we want to identify A, which is 1 in this case. Nothing written there, but it's 1. B is negative 7, and C is 6. So we want to use the quadratic, or the b squared minus 4ac to find our discriminant. So b is negative 7 squared minus 4 times a is 1. C is 6. So we're going negative 7 squared, that's 49. Minus 4 times 1 times 6, that's going to be minus 24. 49 minus 24 is 25. If I were to take the square root of 25, so maybe you can remember that the formula was x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. If the discriminant was 25, and I take the square root of that, it's going to be 5, right? So no matter what b is, I'm going to have something plus or minus 5 over 2a. Right here, I can see that I have two answers. One of them is negative b plus 5 over 2a, and the other is negative b minus 5 over 2a, right? This was positive, so when I take the square root of that, I still get positive stuff. So every time I get a positive discriminant, I know that I'm going to have two real solutions. Every time I get a negative discriminant, so pretend that that had been negative 25, and think about taking the square root of negative 25. That's going to be, because of this, it's going to be 5i, right? So this now is an imaginary solution that we would have. We'd still have the plus or minus in front of it, so we have still two solutions. So anytime we have a negative discriminant, let's see, maybe there's a better way to write this, negative discriminant. Anytime we have a negative discriminant, we will have two imaginary solutions. Okay, So if it's positive, then we have 2 real solutions. If it's negative, the discriminant is negative, then we have 2 imaginary solutions. Are there any numbers that are not positive or negative? Do we have any number that is not positive or negative? Well, the answer is 0. 0 is neither positive or negative, so it has its own special situation. When the discriminant is 0, let's take a look at the formula again. Negative b plus or minus the square root of, if that goes to 0, all over 2a, the square root of 0 is 0. Whoops, I erased more than I wanted to. Let me try that again. Okay, there we go. The square root of 0 is 0. So look, if we go negative b plus 0, we get negative b. If we do negative b minus 0, we still get negative b. It wasn't 2 different things that we got there. So if 0 is the discriminant, this is a case where we only get 1 solution. And because it's not imaginary, right, there's no I in there, it's 1 real solution. Okay, this should be enough to help you finish off this assignment and have success with it. Please let me know if you have any questions, and once you do complete it, if you want to see the answer key, let me know so that you can check your work. Okay?